Introduction. Today, Raj and Aman came to the market and now they are enjoying their drinks at the cafeteria. Aman, you always drink Sprite. Yeah, I like only this one. Okay, it has green colored bottle and looks quite nice. Aman, I wanna ask you something. Yeah, sure. How is green colored glass prepared? Okay, Raj, I will tell you. This green color is due to some chemicals added during the manufacturing of glass. Uranium salts are used to impart green color to glass. Okay, and what is uranium? Uranium is a natural element. It is a member of F block elements in the periodic table. Okay, and I want to know more about this. To know more about this, you have to explore the D and F block elements. Students, today we will study about the D and F block elements. Objectives. At the end of this lesson, you will be able to define group 17 elements, explain physical and chemical properties of group 17 elements, describe halides and oxides of group 17 elements, analyze anomalous behavior of fluorine, explain manufacturing and properties of chlorine, know about interhalogen compounds, define group 18 elements, explain physical and chemical properties of group 18 elements. D block elements, transition elements. The D block elements are those in which last electron enters the D subshell of penultimate shell. The elements of D block of periodic table are also known as transition elements as they are placed between S and P blocks. These elements possess properties that are transitional between the S and P block elements. The transition elements may be defined as the elements whose atoms contain partially filled d orbitals. There are 4 series of transition elements spread between groups 3 to 12. The general electronic configuration of these elements is N-1 D1 to 10Ns1 to 2. Electronic configuration. In the transition elements, d orbitals of penultimate shell are successively filled. There are 3 transition series. The first transition series involves the filling of 3d orbitals. It starts from scandium and goes up to zinc. The second transition series involves the filling of 4d orbitals and includes 10 elements from yttrium to cadmium. The third transition series involves the filling of 5d orbitals. It starts from lanthanum and goes up to mercury. Atomic radii and ionic radii. Atomic radii. Atomic radii of transition elements in a period smaller than S block elements and larger than P block elements. In a series, atomic radii decreases initially and varies irregularly, showing near consistency till 11th group and then increases in the 12th group. With increasing atomic number, nuclear charge and shielding effect of d electrons increase and counterbalance the effects, resulting in small decrease in atomic radii. In zinc, cadmium and mercury, there is increase in atomic radii due to electron repulsion which exceeds the nucleus' outermost shell attraction. Ionic radii. Ionic radii decrease from left to right. It decreases with increase in oxidation state. For the same oxidation state, the ionic radii generally decreases with increase in nuclear charge. General characteristics of transition metals. Metallic character. Transition elements are malleable and ductile metals having metallic luster. These are good conductors of heat and electricity. Except mercury, all are solids. Atomic volume and density. They have low atomic volume and high density. Melting points and boiling points. They are directly related to the strength of metallic bonds, which in turn depends on the number of unpaired electrons. It rises to the maximum and then decreases in a period. It increases in a group. Tungsten has the maximum melting point. In tungsten, partially filled d orbitals form additional covalent bonding due to de-overlapping of adjacent atoms. Ionization energy. The ionization energies of transition elements are higher than those of s-block elements but lower than p-block elements. In a particular transition series, ionization energy increases gradually as we move from left to right. The increase in ionization energy is primarily due to increase in nuclear charge. 5D transition elements possess higher ionization energies than 3D and 4D transition elements. This is due to the greater effective nuclear charge in these elements because of the ineffective shielding of the nucleus by 4f electrons. Oxidation states. All transition elements except first and last number of the series exhibit variable oxidation states. The maximum oxidation state shown by first series increases from scandium to manganese and then decrease. The common oxidation state of first series is +3. The compounds of transition elements in lower states +2 and +3 are mostly ionic and of higher oxidation states are covalent. For example, ZnCl2 and CdCl2 are ionic in nature and Cr2O7 and MnO4 are covalent in nature. Transition metals with fluorine and oxygen exhibit higher oxidation state due to higher electronegative nature of fluorine and oxygen. Standard electrode potential. Electrode potential is the electric potential developed on a metal electrode when it is in equilibrium with a solution of its ions, taking electrons from the electrode. There is irregular variation in electrode potential due to irregular variation in ionization enthalpy, sublimation energy, and energy of hydration. The E0 value decreases from left to right across the series. Manganese, nickel, and zinc have higher values than expected because of their half-filled or completely filled 3d orbitals in case of Mn2+ and Zn2+, and the highest negative enthalpy of hydration Ni2+. Reducing properties. The electrode potential of the first transition series metals are quite high. Hence, they are expected to be oxidized easily to their ions. Hence, they should be good reducing agents. But they are not, because of their high heat of vaporization, high ionization potentials, and low heat of hydration. Since the oxidation potential of copper is negative, it has a low tendency to change to Cu2+ ions and does not displace H+ ions from acid solutions. Magnetic properties. The substances which contain some species with unpaired electrons in their orbitals behave as paramagnetic substances. The transition metal ions generally contain one or more unpaired electrons in them, and hence their complexes are generally paramagnetic. The paramagnetic character increases with increase in number of unpaired electrons. It is expressed in terms of magnetic moment. The magnetic moments of the elements of first transition series can be calculated with the unpaired electrons by the spin-only formula. complex formation. Transition elements have great tendency to form coordination complexes with Lewis bases. These groups are called ligands. A ligand is normally a neutral molecule or a negative ion. For example, FeCN6 4 negative, NiCN4 2 negative, and PtCl4 2 negative. Great ability of transition metals to form complexes is because of the fact that they have small size, they are highly charged ions, they have vacant low energy orbitals to accept lone pairs of electrons donated by ligands. Complexes in which metal is in +3 oxidation state are generally more stable than +2 oxidation state. Formation of colored ions. The transition metal ions and their compounds are usually colored. In a free isolated gaseous transition metal ion, 5 d orbitals are generated. In real situation, the ion will be surrounded either by solvent molecules or by ligands. Surrounding groups affect the energy of d orbitals, and normally they split up into two sets of d orbitals having different energies. This corresponds to a fairly small energy difference, and therefore light is absorbed in the visible region. So, when white light falls upon these complexes, they absorb wavelength of a particular color for promotion of electron, and substance appears to be of complementary color. Catalytic properties. The catalytic activity of transition metals may be due to following reasons. Transition metals with their variable valencies may form unstable intermediate compounds, providing a new path of lower activation energy for a reaction. For example, iron catalyzes the reaction between iodide and persulfate ions. Transition metal provides large surface area with free valencies on which reactant molecules get absorbed. This has the effect of increasing concentration of reactants on catalyst surface and also weakening of bonds in reacting molecules. Many transition metals and their compounds are known to catalyze a number of reactions. For example, palladium is used as a catalyst for hydrogenation. Titanium trichloride is used as Ziegler-Natta catalyst in the production of polythene. Iron is used in Haber's process for the manufacture of ammonia. Nickel is used as catalyst in numerous reduction processes. Formation of interstitial compounds. Transition metals form a large number of interstitial compounds in which small atoms are trapped in the vacant interstitial sites of transition metal crystal lattice. Bonds present in them are neither typically ionic nor covalent. For example, Mn4n and Fe3H. Presence of small atoms in the crystal lattice decreases malleability and ductility of transition metal but increases its tensile strength. For example, cast iron and steel are hard due to the presence of trapped carbon in the interstitial spaces. They have high melting points and are chemically inert. Alloy formation. An alloy is a homogeneous hybrid of two or more elements, at least one of which is a metal, where the resulting material has metallic properties. It has different properties from those of its compounds. Transition elements have almost similar atomic sizes. Therefore, these elements can mutually substitute their positions in their crystal lattice, and many alloys are possible between transition metals. For example, brass, bronze, and various types of steel. The alloys so formed are relatively hard and possess higher melting points. Some important compounds of transition elements. The transition metals react with non-metals such as oxygen, nitrogen, halogens, sulfur, and carbon to form binary compounds. Some of these compounds find important industrial applications. Metals of first transition series form a variety of oxides in which the metal exists in different oxidation states. These oxides may be acidic, basic, or amphoteric in nature. Stable oxides have been shown in bold type. A indicate acidic, B indicate basic, and C indicate amphoteric nature of the oxide. These oxides are generally formed by heating the transition metal with oxygen at high temperature. Oxides are basic when metal is in lower oxidation state and acidic when in higher oxidation state. When metal is in intermediate oxidation state, oxides are generally amphoteric. The highest oxidation state in oxides of any transition metal is equal to its group number. As oxidation number of a metal increases, ionic character of the oxide decreases. Basic and amphoteric oxides dissolve in acids and bases, forming oxocationic salts. Potassium dichromate, K2Cr2O7. It is prepared from chromite ore. Ore is powdered and fused with Na2CO3 in excess of air when sodium chromate is formed and CO2 is evolved. Fused mass is then extracted with water when sodium chromate, being soluble in water, passes into solution and Fe2O3 is left behind. Sodium chromate solution is treated with sulfuric acid when sodium chromate is converted into sodium dichromate. Sodium sulfate, being less soluble, crystallizes out as decahydrate and is removed by filtration. Solution of sodium dichromate is heated with a calculated amount of potassium chloride when potassium dichromate, being much less soluble than sodium salt, crystallizes out on cooling as orange-red crystals. Properties of potassium dichromate. It is an orange-colored crystalline solid with a melting point of 670 Kelvin. It is moderately soluble in cold water but appreciably soluble in hot water. It decomposes to give oxygen when heated to high temperature. It acts as a strong oxidizing agent in acidic medium. When any chloride is heated with solid K2Cr2O7 and concentrated H2SO4, orange-red vapors of chromyl chloride are formed. When these vapors are passed into NaOH solution, it turns yellow due to the formation of Na2CrO4. Acidified solution of dichromate ions forms deep blue color with H2O2 due to formation of CrO5 CrOO2 2. Interconversion of chromate into dichromate. Chromate ion is tetrahedral, whereas the dichromate ion consists of two tetrahedra sharing one corner with chromium-oxygen-chromium bond angle of 126 degree. There is an equilibrium between chromate and dichromate ions at a pH of about 4. They are interconvertible in aqueous solution depending upon the pH of solution. Chromate ions change into dichromate ions on adding acid, while dichromate ions change into chromate ions on adding alkali. Oxidation state of chromium is dichromate and chromate is same. Potassium permanganate, KMnO4. Potassium permanganate is an inorganic chemical compound with the formula KMnO4. It is a salt consisting of K positive and MnO4 negative ions. It is obtained from pyrolurite, a black color powder. Pyrolurite is fused with KOH and air. This produces a green color potassium manganate. Commercially, it is prepared by an electrolytic oxidation of an aqueous solution of K2MnO4. Manganate and permanganate ions both are tetrahedral. Green manganate is paramagnetic with one unpaired electron, but purple permanganate is diamagnetic. Properties of potassium permanganate. Potassium permanganate is purple-black colored crystalline solid with a melting point of 523 Kelvin. It is soluble in water. Its aqueous solution has purple color if concentrated, but if the solution is dilute, it has pink color. On strong heating, it decomposes to give oxygen. On heating with alkali, potassium permanganate changes into potassium manganate and oxygen gas is evolved. It is a very strong oxidizing agent in both alkaline and acidic medium. Uses of potassium permanganate. The important uses of potassium permanganate are following. It is used as a disinfectant and germicide. A very dilute solution of KMnO4 is used for washing wounds. It is used as an oxidizing agent in laboratory and industry. It is used as oxidant in preparative organic chemistry and as Beer's reagent. It is used for purifying water of stinking wells. It is used in the volumetric estimation of ferrous salts, oxalic acid, and oxalates. F-block elements, the inner transition elements. In F-block elements, the last electron enters the anti-penultimate energy level, that is n-2 f orbitals, where n can be 6 or 7. The last electron also called as differentiating electron. These elements are also called inner transition elements because n-2 f orbitals lie deep within, inner to the penultimate shell. The general electronic configuration of these elements is n-2 f1 to 14, n-1 d0 to 1, ns2. The inner transition elements have been divided into two series, lanthanoids and actinoids, depending upon the fact that whether the differentiating electron enters a 4f orbital or a 5f orbital. The lanthanoids. When differentiating electron enters one of the 4f orbital, the element is said to be belonging to the first series of inner transition elements. 14 elements after lanthanum belong to this series. These are called lanthanoids as they appear immediately after lanthanum in the periodic table. The atoms of these elements have electronic configuration with 6s2 common but with variable occupancy of 4f level. It is energetically favorable to move single Fd electron into 4f level in most of the elements. Cerium, gadolinium and lutetium has 5d1 arrangement because they leave a half-filled 4f level which gives increased stability. Physical properties of lanthanoids. All lanthanoids are soft and silvery white metals. Some properties of lanthanoids are following. Color. Many trivalent lanthanoid ions, Ln3+, are colored both in the solid state and aqueous solution. The color seems to depend on the number of unpaired F electrons and arises from F to F transitions. For example, Pr3+ is green and Pm3+ is pink. Density. Lanthanides have high densities ranging from 6.77 to 9.74 gram per centimeter cube. It increases with increase in atomic number. Melting points and boiling points. Lanthanides have fairly high melting points and boiling points, and these increase with increase in atomic number. This is because the attraction between atoms increases as the size decreases. Chemical properties of lanthanoids. Oxidation state. The sum of first three ionization energies is low, and therefore the most common and stable oxidation state is +3. Magnetic behavior. Ln3 plus ions are generally paramagnetic due to the presence of unpaired electrons in f orbitals. La3 plus and Ce4 plus have an F0 configuration and Lu3 plus has an F14 configuration, therefore they are diamagnetic. Chemical behavior. Early members of the series are quite reactive, similar to calcium, but with increasing atomic number, they behave more like aluminium. Lanthanoid contraction. The atomic radii and ionic radii of tripositive lanthanoid ions show a gradual decrease down the group. Although the atomic radii show some irregularity, but ionic radii steadily decreases down the group. The additive effect of contraction over 14 lanthanoid elements is quite appreciable. This is known as lanthanoid contraction. As the atomic number increases in lanthanoid series, for every proton added to the nucleus, the extra electron goes to fill 4f orbitals. 4f electrons constitute inner shells and therefore are not so effective in shielding the nuclear charge. Therefore, electrons are pulled closer to the nucleus due to shrinking of electron cloud. This results in gradual decrease in size of lanthanoids with increase in atomic number. Uses of lanthanoids. These metals are not much used. The important uses of lanthanoids are following. The unseparated mixture of lanthanum and lanthanides is called mixed metal. It contains about 50% cerium, 40% lanthanum, 7% iron, and 3% other metals. This is added to steel to improve its strength and workability. Mixed metal is also used in small amounts as lighter flints. La2O3 is used in Crookes lenses which give protection from ultraviolet light by absorbing it. CeO2 is used to polish glass. CeSO4 is used as an oxidizing agent in volumetric analysis. The actinoids. The series of elements involving the filling of 5f orbitals is called actinoid series. They follow actinium and include the 14 elements from thorium to lawrencium. They are so called because they come immediately after actinum in periodic table. They are also known as second inner transition series. They have electronic configuration of 7s2 and variable occupancy of 5f and 6d subshells. The actinoids are radioactive elements. The earlier members have relatively long half-lives and the latter ones have half-life values ranging from 1 day to 3 minutes. Properties of actinoids. All actinoids are silvery white metals. These elements are radioactive. After uranium, all the elements are man-made. They have high densities. Their melting points are moderately high but are considerably lower than those for transition elements. Ionic size. The size of ion decreases regularly along the series because the nucleus is poorly shielded by f electrons. This is known as actinide contraction. Oxidation state of actinoids. They have an oxidation state of +3. However, this is not always the most stable oxidation state in them. The most stable oxidation states for the first 4 elements are thorium +4, protactinium +5, uranium +6, and neptunium +5. Plutonium shows all oxidation states from +3 to +7, but the most stable is plutonium +4. For americium and the remaining actinides, +3 is the most stable oxidation state. Uses of actinoids. The important uses of actinoids are following. Thorium is used in atomic reactors to generate power. Thorium is also used in the treatment of cancer. Uranium is used as nuclear fuel in reactors. Uranium salts are used to impart green color to glass. Plutonium is used as fuel in atomic reactors and also for making atom bombs. Difference between lanthanoids and actinoids. In lanthanoids, last electron enters into 4f orbital, whereas in actinoids, last electron enters into 5f orbital. In lanthanoids, general electronic configuration is 4f0 to 14,5d0 to 16s2, whereas in actinoids, general electronic configuration is 5f0 to 14,6d0 to 17s2. In lanthanoids, the decrease in atomic size is not regular, but the decrease in size of tripositive ion is regular. Whereas in actinoids, there is gradual decrease in the atomic and ionic size. In lanthanoids, the principal and common oxidation state is +3. Some elements also show +2 and +4 oxidation states. Whereas in actinoids, the common oxidation state is +3, but it is not always the stable state. Lanthanoids do not form complexes readily, whereas actinoids have much greater tendency to form complexes. Compounds of lanthanoids are less basic, whereas compounds of actinoids are more basic. Lanthanoids are non-radioactive except promethium, whereas actinoids are all radioactive. Did you know? Iron was believed to have been first discovered by the Egyptians in 4000 BC. The widespread use of this element led to the period in world history called the Iron Age. The term carat, meaning purity, is used to indicate the amount of gold present, with 24 carats being pure gold and lower ratings proportionally less. Henry Antoine Becquerel discovered that uranium was radioactive in 1896. Summary. Let us summarize what we have learnt. The d block elements are those in which last electron enters the d subshell of penultimate shell. Atomic radii of transition elements in a period smaller than s block elements and larger than p block elements. In a particular transition series, ionization energy increases gradually as we move from left to right. Electrode potential is the electric potential developed on a metal electrode when it is in equilibrium with a solution of its ions, taking electrons from the electrode. The transition metal ions generally contain one or more unpaired electrons in them, and hence their complexes are generally paramagnetic. Potassium permanganate is obtained from pyrolurite, a black color powder. Pyrolurite is fused with KOH and air. This produces a green color potassium manganate. The series of elements in which differentiating electron enters one of the 4f orbital are known as lanthanoids. The series of elements involving the filling of 5f orbitals is called actinoid series.